Hi, I'm Kyoungmin from Postech. I present an in-depth study about learned cardinality estimation. The cardinality estimation is to estimate the number of query results on a database. This can be used for approximate query processing or in query optimization in RDB methods. We focus on select join queries. Our query queue has a set of tables, joins, and selection predicates. A selection predicate is defined on a single attribute A. The domain is the set of all attribute values of A. An array is the range of A specified by this predicate. So it's a subset of the domain. A query is then a hyperrectangle. If a database has attributes A1 and A2, we can visualize the domains in two axes and the ranges for a query. Their characterization product, a hyperrectangle here, corresponds to the query range. Traditional methods include sampling. For example, we can sample some tuples from the base tables, join them, and estimate the full join size. Or we can build summaries, for example, such as histograms. Learned methods are classified into query-driven and data-driven methods. Query-driven methods solve a regression problem from query features to cardinality. Therefore, they are supervised. Data-driven methods solve a density estimation problem in an unsupervised way. They learn the joint probability distribution over all attributes. Then, given a query queue, it estimates the query density, which is the density of the hyperrectangle. Here. Then, the cardinality can be computed as the product of the full join size and the query density defined over this way. However, previous learned studies have limitations. They use single table data sets only, or a small subset of real data, or compare few models or traditional methods only. And they regard the models as black boxes without a deep understanding of why large errors occur. So it's uncertain whether we can answer to the following question. Is learned cardinality estimation ready for production for real and complex data? From this motivation, we made the following contributions. First, we provide the taxonomy and unified workflow of both query-driven and data-driven methods. We present new methods that outperform state-of-the-art. We conduct fair and comprehensive evaluations and demystify the black box models. We inject the learned cardinalities into a DBMS and see if they can improve the plan quality. Finally, we summarize the lessons learned and propose new research opportunities. Here, I explain a few items, and each item will not be fully explained. So, for more explanations, please see our paper. First, I explain the taxonomy. You can see the estimator dimension and the category where it belongs to a query-driven or data-driven method, and the learning approach, the model architecture, the tail group dimension, I'll explain sooner, and inductive bias. This is the set of assumptions that a model uses to predict an unseen query. The first method, FCN, is the fully connected network. It's a query-driven method and takes all selection predicates for all attributes and outputs cardinality. The network here is intended to strong capture the inter and intra-table predicate correlations. It captures the interactions between all predicate pairs. MSDN is multi-set convolutional network. It weakly captures the correlations because it uses a shell layer convolution for each set of tables, joins, and selections then uses pooling to aggregate its set. This pooling does not strongly capture the interactions between the set elements. And FCN is found to be more accurate than MSDN on single table dataset because FCN better captures correlations. However, MSDN performs well on large databases because it has fewer number of parameters and is more prone to overfitting. To take their benefits, we implement this FCN plus pool model. We use FCN per table and fling across tables to capture this intra-table correlations well, but not to increase the number of parameters. NeuroCard is a data-driven method that uses deep autoregressive model, we call DAR, and given an attribute order, it takes attribute values from A1 to some AI-1 and outputs the conditional distribution for AI, given the previous values. Then it estimates the query density by factorizing it into the multiple conditional densities given some sample. So if we have 3 attributes, we have 3 factors given this sample A1, A2. TipDB is a data-driven method, uses some product network as PN. It's basically a tree of subtables. And here we start with an initial sample of the joint table. If the columns seem independent, it splits columns. So the columns in this region is regarded independent to the columns in this region. If no columns seem independent in this region, it splits the rows instead. So in this region, it groups similar rows to make the columns in its subregion independent. So it repeats this column and row split until its region contains only one attribute. Here, a color represents an attribute and size represents the density. And inference is done by multiplying and adding the densities of these query relevant regions. Here, I now explain this table group dimension. This dimension is either 1 or n. If it's 1, like NeuroCard, a single universal model is built for all tables. If it's n, like DeepDB, a small model is built for each subset or a group of tables. So multiple models can be used if a query is large. And here are some better methods. As explained before, FCN plus pool often outperforms other query-driven methods. In DeepDB plus JSP, this JSP part removes the bias in the sample data, which is used for training. And training this unbiased data generate more accurate models. Third, fair and comprehensive evaluations. And here's the table of our training databases and workloads. We use sub-databases of IMDb and TPCS of different sizes, where we have small, medium, and large size databases for IMDb. And you can see the number of tables, rows, and columns in the full join table. For workloads, we have a synthetic workload with the same name as the training database, like WIMDB small. This is generated from the corresponding database. And small workloads can be estimated by the models trained on larger databases, such as we can use inference these small queries on medium and large databases. And here are some key results. We use a small workload on 3 training databases. The triangle corresponds to the small database, square to the medium, and circle to the large. X-axis is the median inference time, and y-axis is the median error. And you can see that data-driven methods here have smaller error than the query-driven methods here, but they have large inference time. On the large database, the circles, the query-driven methods have large errors because there are so many patterns to memorize, which leads to a low generalizability. DeepDB, however, is robust on large database because it groups tables and builds small and robust models for each table group. And here's the model size and training time. Data-driven methods have large model size, which because of their data-dependent sizes. And large model size typically lead to a large training time. We also vary the number of tables in the test queries from 1 to 6. And DeepDB variants here with table grouping have an additive and increasing error because the large queries need multiple models and more independence assumptions between the models are used. Neural card without table grouping have a subtractive and decreasing error because after training a universal model, the small queries need some kind of normalizing factors. And these normalizing factors have large variances. I'll explain it soon. And we demystify this black box model. We use also synthetic single table datasets with varying skew and correlation. In the first law, the skew increases, and in the second law, the correlation between the attributes increases. And at medium to high skews, these medium size and irregular regions increase the error, and at higher skews, these large size and regular regions decrease the error. And at correlation 0, you can see that all attributes are independent and column splits are enough to build the model. However, as the correlation increases, more low splits occur, and these small regions increase the error. So, as the correlation increases, the error increases. This figure shows how neural code works for occurring. This x-axis is the sample, and y-axis is the log of the density or a normalizing factor explained before. The black dotted line is the true query density. The solid black is the estimate. You can see that it is underestimated and has a large variance. We break down this estimate into this conditional densities and normalized vectors, where conditional densities have large biases and vectors have large variances. These two are key sources of the neural code error. And these such patterns occur on queries with highly selective predicates, where most attribute values are unseen at training, so they are assigned low densities. Again, we show our contributions again, and please find more interesting things in our paper. Thank you for listening.